Today, we're exploring an exciting combination: Google Cloud's BigQuery and Jupyter Notebooks. BigQuery is an extremely powerful data warehouse that can handle almost unlimited amounts of data, while Jupyter Notebooks are considered the gold standard for data analysis. We'll learn how to get the best of both worlds by doing analysis in Jupyter while taking advantage of BigQuery's massive processing power. One of the best things about this approach is that it works with any kind of Jupyter notebook you prefer. Whether you use Google Colab, run notebooks on your local computer, or use a managed notebook service, the principles we'll discuss will work everywhere. For our demonstration today, we'll use something called Vertex AI Workbench, but don't worry if you use something else. You can easily apply these concepts to other notebook environments. Let's begin by setting up our environment. First, go to the Google Cloud Console and either create a new project or select an existing one. Navigate to Vertex AI and enable all the recommended APIs. This is a simple first step to get started. Next, we'll go to the Workbench service. It's worth noting that Google Cloud offers many different notebook options, including Google's own Colab and Colab Pro. While we've discussed the advantages and disadvantages of these options in other videos, today we're focusing on Workbench because it's the best way to demonstrate implementation-independent Jupyter notebooks. Before we create our notebook, there's an important cost consideration to keep in mind. The default setup costs about 20 cents per hour to run. If you're working with a limited budget, you can reduce this cost by choosing a smaller machine size or selecting a different region. For our demonstration purposes, though, the default settings will work perfectly. After setting up the notebook, click to open it, and you'll see the familiar web-based Jupyter interface. There's something special about this setup. It uses the default Compute Engine service account. This might sound technical, but it's actually a helpful feature that makes our lives easier. Thanks to Google Cloud's Identity and Access Management, or IAM system, we can access BigQuery directly from our notebook without dealing with complicated authentication processes. Now that we have our notebook ready, let's prepare some data to analyze. When working with this type of setup, it's important to use BigQuery for data storage because it's extremely good at handling and running many queries at once across large amounts of data. Our Jupyter Notebook, in comparison, has limited resources and isn't designed for processing huge amounts of data. In a typical real-world scenario, you would use an infrastructure as code tool like Terraform to set up these components, things like your notebook, identity settings, and BigQuery datasets. Terraform is excellent for automating and managing cloud resources. However, to keep things simple for this demonstration, we'll create everything directly in the Google Cloud Console. Let's start by going to the BigQuery page to create our dataset. We'll give it a straightforward name, Demonstration. For the location, we'll select US Multi-Region. After clicking Create, we have our new dataset ready to use. The next step is to create a table within this dataset that we can analyze in our Jupyter Notebook. We'll use an example dataset that comes as an Excel file. This presents an interesting challenge. The file is fairly large at about 22 megabytes, and since Excel files are proprietary formats, we need to convert it to something BigQuery can work with more easily, like a CSV file. For files that aren't too large, Google provides a simple solution. We can upload the Excel file to Google Docs and then download it as a CSV. Interestingly, when we do this conversion, the file size increases to about 40 megabytes. That's almost double the original size. Don't worry though, as BigQuery can handle this easily. Now we're ready to create our table in BigQuery. We'll upload the CSV file from our local system. One of BigQuery's helpful features is its ability to automatically detect the schema, or structure, of our data, so we don't have to specify it manually. Our dataset contains retail information, which will work well for our example analysis. However, we encounter our first challenge. BigQuery reports an error related to the datetime fields in our data. This is a common issue when working with data, but it's easily fixed. We need to adjust the format to use a more standard datetime format. After making this adjustment and re-exporting the CSV, we can try importing it into BigQuery again. Let's examine the schema of our new retail table. While most of the data types look logical, we notice something interesting about the invoice number and stock code fields. At first glance, they might seem like they should be integer fields, but when we check the preview, we see that both fields sometimes contain letters, not just numbers. This confirms that BigQuery made the right choice in how it interpreted these fields. Now comes the exciting part, where we can use our Jupyter Lab notebook to analyze this data. We'll start fresh to give you the complete experience. One of the most powerful features we'll use is something called BigQuery Magic. When you type BigQuery in a notebook cell, you can run native BigQuery queries and automatically save the results in your Python environment. This creates a seamless bridge between BigQuery's powerful data processing and Python's analysis capabilities. Let's start by creating a clean version of our table. While you can write BigQuery SQL queries directly in your notebook, you get some nice benefits like autocomplete and better syntax highlighting if you draft them in the BigQuery console first. Either way, the SQL code works the same. After running our query in the notebook, we can check our demonstration dataset and find our new Retail Clean table, which contains aggregate information organized by customer IDs. Next, we'll create some features for machine learning. We can do this with another BigQuery block, essentially creating layers of our data using SQL queries that we keep versioned in our Jupyter Notebook. After running these queries, we'll have a new ML table that's well structured for machine learning, including various features we've designed and even test validation and training splits. While we've been running individual queries so far, Jupyter's real strength lies in its visualization capabilities. Let's analyze the days since last purchase from our ML table. When we save this data to a variable called Regency, it automatically becomes a Pandas data frame, one of Python's most powerful tools for data analysis. This seamless integration means we can immediately use all of Pandas' capabilities to analyze and visualize our data. However, we noticed something odd in our analysis. The frequency data isn't showing much variation. Everything seems to cluster around a single value. Looking deeper into our ML data, we see the number of purchases is consistently around 1, and the days since purchase doesn't look quite right. Checking our clean data reveals everything is converging to the same date, suggesting an issue with our data export. Looking more closely at our data, we have the correct number of records, 541,000, but the dates aren't being processed correctly. Instead of trying to fix this in the CSV export process, we can handle this directly in Python. The good news is that when we extract the invoice dates directly from our Excel file, they display correctly, even though they're in string format. After ensuring all the schema types match what we expect, particularly confirming that customer IDs are integers, We can push this corrected data back to BigQuery. After this data cleansing and type adjustment process, we have a new retail table with properly formatted dates. When we preview the data now, we can see different invoice dates appearing as expected, which is exactly what we wanted. One of the beautiful aspects of having all our queries saved as code in our Jupyter Notebook using BigQuery Magic is that we can easily recreate our derived tables. We can run through the process again to generate our clean data and then our ML data with the corrected dates. When we analyze the results now, we see much more realistic patterns. The days since last purchase shows more natural variation, and the frequency analysis reveals much more interesting patterns in customer purchasing behavior. Let's look at some key principles we've learned. First, the BigQuery Magic command is essential for smoothly combining Pandas and BigQuery analysis. Next, when we need to save derived data back to BigQuery, we can use the toGoogle BigQuery method on our data frames. Additionally, it's important to leverage BigQuery's massive scalability. This means doing less processing in Jupyter and focusing more on visualization there. Although we're using Google Cloud tools, these principles apply to other cloud platforms too. For example, if you were using AWS, you'd use AWS's identity system, SageMaker for notebooks, and Amazon Redshift for data warehousing. The concepts remain the same. Finally, let's consider some architectural improvements. BigQuery's BI engine, an in-memory cache layer, could significantly improve query performance for large systems. If you're focusing on machine learning, you might also consider integrating your ML data table with Vertex AI's artifact and dataset management system for a more streamlined machine learning workflow. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all the code and diagram files in the description as well. Thank you very much for watching to the end, and please enjoy responsibly.